We are studying the properties of differentiable maps. In particular, we want to know whether some interesting properties, as for instance being an immersion, is an open property. Or in other words, whether if we have a differentiable map that satisfies such a property, then it is also satisfied by differentiable maps that are close to the first one. Besides that, we are also interested in knowing whether some of these properties are dense, or in other words, whether we can perturb a little bit any differentiable map and transform it into a map that satisfies the property. So we have to consider these two problems: understanding under what conditions some of the properties we are interested in are open, and also under what conditions they are dense. The openness part, we are going to discuss it today in this lecture, whereas the second part, the dense part, we are going to discuss it in a future lecture. Let us define homotopic maps. Consider F0 and F1 continuous maps from a differentiable manifold M to a differentiable manifold N. We say that these two maps are homotopic if there exists a continuous map, capital F, from M times the closed interval 0, 1 to N, such that capital F applied to x0 is f0 of x, and capital F applied to x1 is f1 of x for every x in the manifold M. In this way, we have defined when two maps are homotopic. But if our two maps are differentiable and the homotopy F, capital F, is also differentiable, then we say that F0 and F1 are differentially homotopic. So we have introduced two different notions: homotopic and differentially homotopic. Of course, differentially homotopic implies homotopic, but the other implication is not so obvious. A differentiable map F1 from M to an Euclidean space Rn is differentially homotopic to the constant map equal to 0. And the homotopy is very simple. Is the map capital F from M times the closed interval 0, 1 to Rn that sends the point xt in the product of t and f1 of x. And this is obviously a differentiable map. We are going to use the notation ft for the map defined when we fix the variable t, when we give a specific value to the variable t. And indeed, what we get is that ft of x is capital F applied to xt. In this way, we have defined a map from the closed interval 0, 1 to the set of continuous maps from M to N that sends t in ft, right? Of course, if we consider, for instance, a differentiable homotopy, then we can actually consider here, for instance, C1 maps from M to N, right? And in this way, homotopy can be interpreted as a path of maps. Homotopy defines an equivalence relation in the set of continuous maps from M to N. That's not that's not difficult to prove, actually. And moreover, differential homotopy defines an equivalence relation in the set of differentiable maps from M to N. These proofs are very similar to the proof that homotopy of paths, something that we need in order to define the fundamental group, defines an equivalence relation. the proofs are very similar to that one. So we have two different equivalence relations, at least a priori. And we are going to say that the classes of equivalence for homotopy are called homotopy classes, and the classes of equivalence for differential homotopy are going to be called differential homotopy classes. But there is here a remark to make, and it's that in practice, differential homotopy class is almost never used. And the reason is that we are going to see that if we have two differentiable maps that are homotopic, they're also differentially homotopic. So it is clear that if two maps are differentially homotopic, then they are homotopic, but it also works the other way around when the two maps are differentiable maps. And so these two equivalence relations are the same in the set of differentiable maps. And because of that, we just need to consider one of them. Now we are going to see our first approximation to a stability. Later on, after defining topologies in function spaces, we are going to have a preciser one, a better approach than the one that we are introducing. But this one is just to understand the basics of stability. So stability for a given property on a map F just means that the property still holds for the maps near F. Sure, the big question here is what does it mean to be near F? And so in order to bypass this problem, we are going to use homotopies. Okay? We are going to say that if we're going to define proximity by using homotopies. That's indeed the continuous approach to this problem in which we are considering paths joining different differentiable maps. And there is another approach, as I was remarking, and it is that we can define topologies in the set of differentiable maps. And that's the discrete approach that we are going to see later on. For the moment, we are going to focus on the approach using homotopies. So our first definition of stability, not the last one, it's later on we are going to give a better definition, is that first consider a property defined in the set of CR maps from M to N, where M and N are differentiable manifolds. And we say that the property is stable if whenever we have a map that satisfies this property and we have a CR homotopy, capital F, in which F0 is our map, the map that we are considering, then the property is also satisfied by Ft if t is close to 0. So in this way, we don't define a topology in the set of differentiable maps because indeed what we are doing here is using the topology that it is naturally defined in the closed interval 0, 1. Okay? We're going to see some examples. We are going to consider indeed maps from the line to the plane. In other words, we're going to consider curves. And the properties that we are going to consider now are namely going through a fixed point and then intersecting the x-axis, okay? These properties are not stable because if we have this curve over here going through this point, we can perturb a little bit this curve by using a homotopy, and what we're gonna get is a curve that does not go through that point. And so the property is obviously non-stable, because we can actually show that for all values of some deformation in the example, for this example, we can consider deformation such that for all values close to zero, but different than zero, the curves don't go through this point. Analogously, intersecting the x-axis is not a stable property. In here, we have a curve that intersects the x-axis in just a point, but we can perturb it in a way that these nearby curves do not intersect the axis anymore. And so, again, the property is non-stable. A good example of stable property is transversal intersection. If we consider the x-axis and then a curve that intersects such an axis transversally, and we perturb this curve f0 a little bit, what we're gonna get is not just that the two curves, the perturbation of f0 and the x-axis continue to intersect, but moreover, if the homotopy is differential, we're gonna get that the intersection is still transversal. And so this is the kind of property that it is going to be stable by deformation. Okay? We are going to show the next theorem that says that the following properties are stable in the space of differentiable maps from a compact manifold M to a manifold N. The manifold N is not necessarily compact. And these stable properties are being an immersion, being a submersion, being a local diffeomorphism, being a map that is transversal to a fixed closed submanifold of N, being an embedding, and finally being a diffeomorphism. Okay. Before actually starting the proof of the theorem, let's point out that if we consider, for instance, two curves in R3, our theorem suggests that the intersection is never going to be transversal, because it's relatively simple to deform one of the curves so that the intersection of the two curves is empty. And since transversal intersections are stable, that means that the intersection of two curves in R3 can never be stable. But of course, we already knew that, since the dimension of these submanifolds has the sum of the dimensions is 2, and the dimension of the ambient space is 3, the intersection is never transversal. Okay? Here, we have something that is interesting, is that transversality implies stability. But you can have stable intersections that are actually non-transversal. Here we have a couple of examples. In the first one, when we deform a little bit this submanifold, what we get is that there is no intersection anymore. And so this intersection over here is clearly unstable. But if we go to the second case, the intersection of these two curves is non-transversal, because the two curves, for instance, are tangent at this point. So we have non-transversality, but we have stability. If we deform this curve a little bit, indeed, the two curves are going to intersect anyway. We cannot destroy the intersection by actually considering a small perturbation. So transversality implies stability, that for intersections of submanifolds, but it is possible to have stable intersections that are non-transversal. In this lecture, we introduce the concepts of homotopy and stability, along with some examples, and at the end of the lecture, we actually gave the statement of an stability theorem that we are going to show in our next lecture. Thank you for your attention.